Okay folks, so I'm going to do a root locus now with zeros in it. So in the last video I did a root locus where there were no zeros and we were just poles, and so now I'm going to do one where there are actually poles in the problem, or sorry, zeros in the problem. I'm going to pick from the textbook that I'm using. I'm going to do problem 5.6D. Okay. And so 5.6D is, they don't give you a control block diagram, they just tell you what L is. And so L is S plus 3 over S squared S plus 10. Okay? And so in that case, getting the poles and zeros is fairly simple. So the poles are 0 and 0 and negative 10. So there are 3 poles, so that means n is 3. And then the zeros are negative 3, and so the number of zeros is 1. That means the number of asymptotes, n minus m, is 3 minus 1 is 2. And so that means that we're going to have 2 asymptotes. So that means 2 poles are going to shoot off to infinity, and 1 pole is going to end up at the 0. That's one of the fundamental theorems of root loci, is that every pole, or every zero, I'm not exactly sure how to phrase this, but every pole will have an asymptote towards a 0 if the 0 exists. If there are no zeros, then it just tends off to infinity. So I'm going to draw a big root locus here. And so I'm going to draw 2 poles at the origin, 1 pole at negative 10, and a 0 at negative 3. Now you might look at this and say it's pretty obvious of where everything's going to go, but I mean, it's hard to say, okay? So we're going to do our even-odd thing, right? So even, so there's an even number to the right, and so that's going to give me, this does not exist on the root locus. If you do the phase angle thing, you can draw a vector from here to here, and that's going to give you 180 plus 180, which is 360, so that's not minus 180. The other way you can look at it is you can say that, again, if I put my hand here, the number of poles and zeros to the right is even, and therefore nothing in here is on the root locus. So this part of the x-axis is not part of the root locus. Over here, if I put my hand here, there are 3, which means this part is part of the root locus. Okay? And then if I put my hand here, there are 4 to the right, which means this is not part of the root locus. So I think it's pretty clear that this pole here is going to end up at that 0. Okay, so we figured that in that sense we figured that out. This pole is going to end up at that 0. Now these poles, we need to figure out which way they shoot off. Are they going to shoot off to infinity this way and make the system completely unstable, or are they going to go off to the left? My guess is that this pole is going to kind of push them away, and they're going to kind of come in and shoot off to infinity. That's my guess, at least. There are equations in your book to compute that. So all we need to do is plug those in. So the asymptotes are described like this. So alpha is where the asymptotes intersect on the x-axis, and then phi L are the angles of the asymptotes themselves. So alpha is the sum of the poles minus the sum of the zeros. So sum of the poles minus sum of the zeros all over n minus m. Okay? And so, let me scooch this over a little bit. Break my 3D printer there. There we go. Okay? Then phi L is 360 degrees plus, times L minus 1 over n minus m. Now that is not the equation. That is not the equation that I remember. So, oops. I was looking at the rules for plotting a negative root locus, so that is not right. Let me go back a couple pages. That's dangerous. Let me go back here and see. Let's see. Where are the equations? There it is. Okay. So So it's still, the alpha is still sum of the poles minus the sum of the zeros, but phi L, okay, yeah, I knew this was, something was fishy. This is 180 plus 360 L minus 1 over n minus m. Okay, so let's plug all this in to see what we get. So alpha is sum of the poles, so the poles are 0, 0, negative 10, so that's negative 10, minus the sum of the zeros, they're just 1, so it's negative 3, all over n minus m. N minus m is 2, so it's negative 10 plus 3, which is negative 7, so negative 7 halves, which is about what, negative 3.5? So that means right here, all of the asymptotes are going to intersect the x-axis, okay? Let's look at phi L now. So that's 180 over 2 plus 360 over 2 L minus 1. And that's 90 plus, what, 180? Is that right? Okay. So that means that I'm going to get, for phi 0, I'm going to get 90. Sorry, for phi 1, the first asymptote, I'm going to get 90. And for phi 2, I'm going to get 90 plus 180, which is 270. So that means that the asymptotes look like that, which is actually good news because that means that these poles are going to do this. Now, how do I know that? Well, they're going to, the asymptote is kind of like an attractor, like a rail, like a train track, and so the poles are going to get attracted to that. What this means is that this system is stable always for any value of k, okay? I personally want to check my work. 2 reasons: either I'm wrong, I'm going to reshoot this video, or B, I'm right, and then we'll reinforce our learning here. So I'm going to grab my, my book here, so I'm going to come out of frame here, and I'm going to scan this for my students that are actually learning, or sorry, that are actually enrolled in the class. So I'm going to do beacons here. Okay. And then scan that, 426. Okay, so the way I want to test and see if this is a stable always is I want to do a Routh-Hurwitz table. Okay? And so what I'm going to do is I'm going to keep L and I'm going to erase this. If this is truly stable always, my Routh table will tell me that it's always stable. So remember, my characteristic equation, let me use a different marker here, is 1 plus KL equals 0. So that's going to be 1 plus K S plus 3 over S squared S plus 10 equals 0. And in order to not lose information, I'm going to multiply both sides by S squared S plus 10. And I'm going to get S squared S plus 10 plus K S plus 3 equals 0. And then in order to do a Routh table, I need to factor this out. So I'm going to get S cubed S squared KS plus 3K equals 0. And I could plug this into a root finder if I wanted to, or I'm just going to go ahead and build a Routh table here. So I'm going to say S cubed, S squared, S to the first, S naught, and I'm going to look at all of these. And so I'm going to get 1K, see 1K, skip 1K, and then 0. And then the second row is going to be 10, and then 3K, and then 0. And so we already, 1 and 10 are both positive, so we're already good. We know that we're still stable there. We need to compute this guy, H, and we also need to compute this guy over here. This is going to be, I want to say this is going to be 0. You're going to get 1 and 10, up and to the right is 0, 0, all over 10. And so yeah, so that whole guy is 0. I just need to get H then. So H is going to be the minus determinant of the two numbers above it, 1 and 10. And then up and to the right is going to be K and 3K, all over 10. And so I'm going to get 3K minus, there's a minus in front of it, minus 10K over 10. So that's going to be 10K minus 3K over 10, which is what, 7K over 10? So H is 7K over 10. And then I'm going to do the next column, which is you divide by h. You take the two numbers above it, the next row, 10 and h. Up and to the right is 3k and 0. And so you're going to get 10k times 0 minus 3k times h. The 0 is going to go away. The negative sign is going to cancel the negative sign here on this determinant, and then the h's are going to cancel. And so you're just going to be left with 3k. So the first column then is 1, 10, h, which is 7k over 10, and 3k. And all of these need to be greater than 0. And so if you look at this, that's greater than 0, check. That's greater than 0, check. In order for this to be true, k has to be greater than 0. In order for this to be true, k has to be greater than 0. Which means that as long as k is greater than 0, the system is stable always, which is exactly what we found in that root locus in the last problem, like 3 or 4 minutes ago. Okay, so that's root locus with zeros. Hopefully that helped. And if you have more specific questions, post in the comments and I can do some more problems. Hope you have a nice day.